Okay, so good morning, and thank you for the introduction. So today I'm indeed going to talk about elimination constraints in rock, what you can do and cannot do with them. But first, I'd like to start with a little story. So it's actually something that has happened to me while I was trying to formalize this work in MetaRock. And so I call it kind of meta story, right? So once upon a time, I wanted to define this boxing type of a De Bruijn index. Everything was going well. Everything was compiling, right? But at some point in the code, I wanted to prove the decidable equality of this type. And I was like, okay, so it's going to be easy, right? Because natural numbers have decidable equality. And so I can just use this to say, okay, so if my two De Bruijn indices are equal, then I'm passing them through a function, and I got an equality. If they are not equal, then assuming that the boxing type are equal, then I can just pass them through a projection, and we have an equality of the De Bruijn indices. So I was thinking that this function will compile as is, but it doesn't, right? So what does it say? It says that the constructors I've given are not the right one. They are ones of type sum, while one of type symbol was expected. So I'm like, okay, so what kind of name can someone give something constructors of type sum? I thought of in left and in right. So I wrote it, and once again, I tried to compile. It didn't work. And so I didn't know what to do. I was like, okay, I can't guess anymore what the constructor's name can be. So I capitulated. I asked the enemy, and it told me, but it's left and right. So I wrote left and right, and this time it compiled. So it was kind of difficult, right? So what happened here is that in Rock's type system, we have three different sorts, the sort of strict proposition, and of types. So this is good and all, but it also means that we have a duplication of the inductive types. So here, there are four inductive types that are in a Rock's core library, so the library that is shipped with Rock. And we could even add that to up to 27 with all the combination of S prop, and type. So yeah, it's kind of infeasible, right? But we have a savior, because since Coq 8.19, we can do a polymorphic sum type with this kind of Prenex sort quantification. So here, I'm saying that we have three sorts, the sort of A, the sort of B, and the sort of the sum. And doing this, I can actually define only one inductive for the 27 combination, and we can even instantiate them with the different things that are already in Rock's core lib, right? But when I try to compile this inductive, it compiles, but it says that P-sum is defined. So it's good, but usually when you define an inductive in Rock, you also get the eliminators automatically declared, right? And this isn't the case here. So I was like, okay, so maybe it's because it's a new feature, and it hasn't been done in the code yet, right? So I tried to define my own. I'm saying, okay, so we have a non-dependent eliminator, but that's written my need. So I was like, what happens if I do something like this? It doesn't compile, of course. So what it says is that we cannot actually compile something with a different sort than what was matched on. So here we match on X, which has sort S, and we try to create something in the sort S prime here. And yeah, I mean, it makes sense that it cannot do that, because otherwise we could likely instantiate this eliminator with S prop and type, and it will mean it's inconsistent. So yeah. So now well, before we had to declare all the indicatives by hand, but we had the eliminators. And now we have to declare all the eliminators, sorry, by hand. So it's arguably kind of worse, right? And today, in this talk, I want actually this kind of thing to compile. So this is the end goal, except the last one, because it will mean it's inconsistent. So we don't want that. Okay. So, but first, let me tell you a bit about the current status of ROC elimination system, which works with a binary relation, eliminates 2. So we have that type eliminates to prop, type eliminates to S prop eliminates to S prop, and finally S eliminates to S. So S can be either a ground source, like type prop S prop, or it can also be a variable. And this binary relation is used in the 2 typing rules of elimination. So the match rule and the fix rule, which basically say that if we match an X of sort S and we will return something of sort S prime, and S eliminates to S prime, then we can say that this match is well typed, provided that the things that I've hidden are also well typed. And this is kind of the same thing for the fixed point rule. So what we did was to say, okay, so we only need to generalize this a bit and to say to the user, you can actually populate this binary relation with what you want. And so we have 2 things, the user-defined elimination constraints and also the ground elimination constraints. And it doesn't change the rules a lot. We just have the eliminates 2, which has been replaced with the new binary relation. But there, we could think that, okay, it's done. We have implemented this in ROC, and the user can now do what he wants with elimination constraints, and all is good in the world. But it's not the case, because we actually have some kind of restrictions. So the first one is something that depends on the user, actually. Because, okay, so what happens is that if the user defines these lines, it will populate the partial order. So the first definition adds that S eliminates to prop. The second one adds an elimination constraint that isn't related to ground source, but S prime eliminates to S second. And then we declare a global sort, which is kind of like a local sort, except that we can keep it. And we say that, okay, so type eliminates into this new global sort to kind of create something. And then at some point in the code, we want to define this function, which basically says that we need S eliminates to S prime to get to validate these constraints, and S prime eliminates to prop, and X eliminate to S. But in this case, well, because this is a partial order, this is obviously transitive. So we could have something like this in the graph, but we want to let it explicit for the user. Well, he has to write explicitly that he wants X to eliminate to prop, because here, what happens is that X is not consistent, and eliminating to prop or even S prop means that we want something actually consistent. So if we accepted this, if we accepted this definition, then it would mean that we would say, kind of under the nose of the user, that he is doing something inconsistent, and we don't catch it. So, yeah. So another thing to be aware of is the impredicativity that can come up with the elimination constraints. So we'll say, for the sake of this presentation, that sort is impredicative if we have this equivalence between the sort S at level U and the sort S at level V for every UV universe levels. And so in ROC, S prop and prop are impredicative. And what happens if we put an elimination constraint, prop eliminates to S, or S prop eliminates to S, then we can prove that S becomes impredicative. And for S prop eliminates to S, we can even prove that S is propositionally proof irrelevant, right? But the thing is that S is predicative by default because S is kind of a sort variable. So it can be instantiated to type, to S prop, or to prop. And well, type is predicative. So by default, S is also predicative. So what we do currently is that we totally forbid the user to write prop eliminates to S and S prop eliminates to S. But if we were in a world where we didn't forbid this, so what would happen? Actually, it's not so bad, at least with ground truth, because we kind of have a monomorphization theorem which says that for every definition which has elimination constraints, we take all sorts that all ground sorts that verify this elimination constraint, and we duplicate this definition as much as we can. And yeah, if it was well typed before, it should be well typed after, or if it's something that is nonsensical with the sorts involved, then it will just say it's not possible to define something like this. So this implies equiconsistency with Rock's type theory without elimination constraints. With global sorts, it's a bit more difficult. So we have two cases. If we have S prop eliminates to S, well, it's not so bad because actually what happens is that either we put S eliminates to S prop, and so S becomes S prop, so we don't really care. It's kind of the same case as for the ground sorts one. But otherwise, if S doesn't eliminate to S prop, then it means that S cannot communicate with Rock's ground type theory. And so even if the sort turns out to be inconsistent, but it doesn't matter. With the case, prop eliminates to S is still under investigation. And so, yeah, we still have these user-defined inconsistencies that can pop up with the previous example. Right. So the current implementation, to make a bit of a recap, so what we have now is that we can write S eliminates to S prime for both local and global sorts, but we have three constraints. In that first, for rigid sorts, so sorts introduced by the user also needs to specify all of the constraints. We cannot infer one constraint between any two rigid sorts. And we also forbid prop eliminates to S and S prop eliminates to S. We want to implement a predicativity mark for both of these things. But yeah, we don't know if it's going to be enough for prop eliminates to S. And we kind of also have to assure that S prop eliminates to S implies definitional proof irrelevance for S. So there's still something I haven't talked about in the whole of this talk, is that elimination constraints do not work with singleton elimination, subsingleton elimination. So what is subsingleton elimination? It's when you have inductives with at most one constructor, and we give them large elimination even if they are in prop. So the thing is, the rules that I've written for elimination is not the real rule, because we have this little addition that S has subsingleton elimination, and so this becomes well typed with this. But this is also actually a cheat, because this is not something, well, this is not the real rule, which is more something like split in two. And it says, okay, so if X, if X is in A and A is a record, so it's an inductive with one constructor, then we don't have to verify the elimination constraints. Otherwise, if it's a real inductive, let's say, we still have to verify the elimination constraints. So to conclude, what we have done is that we have implemented this elimination constraint in Rock. And now we can write something like this eliminator, the most generic eliminator for some. And we also have on paper proved the equiconsistency for ground truth. And what we want to do now is to formalize all of this in MetaRock. Of course, we plan to add, and the current status of the formalization is that we are implementing sort polymorphism, and want to allow S-prop eliminates to S with the predicativity mark and the definitional proof irrelevance, and also prop eliminates to S if it's possible. So thanks for your attention.